integration. I don't know if you realize this. And that will do it all. And it's fine to do that, okay? So I'm gonna go through that. Yeah, what was your question?
Yeah, what was the quiz average?
6.5, I think. I don't think it made it over 7. It was 6, I think it's 6.5, but don't quote me on that. I could be wrong. And, because there were several people that didn't take the quiz. And so I'm holding that. I can give that to you if you want it later, but there was some unfortunate, I tried to be nice about that. I want to just mention this. I'd like to go over this quiz with you just because I want to make absolutely certain that you guys know how to do a problem like this. This is not a difficult problem, and it's something on a test. If I did, I would not think twice about you getting it right. It was that straightforward in my opinion. So go ahead and give me the electric field. Now it said short dipole, and if for whatever reason you just use short dipole for the radiation resistance, I still gave you credit. What was the electric field I gave you for this one? And if you messed up, I'd always get this question, are you going to drop the lowest quiz? Yes, I'm going to drop the lowest quiz. There, I said it. I did it.
So quizzes or quiz?
So far it's a quiz, but I mean, the classes go pretty well on average, everybody. All right, now, what was the electric field? Let's just take care of this. I just, anyway.
I sub s,
All right.
e to the negative j 40 pi r, cosine theta over r, or all of it over r.
Cosine theta over r.
Yep. And that's a sub theta.
A sub theta. All right. If the standard electric field, if it varies as a cosine or a sine in angle, you know it's really going to be. By the way, these are new markers. It's going to be from an infinitesimal or short dipole. But that angle, this functional form for the angular variation is either cosine or sine. It is a short dipole, right? That's it. Just has to do with the orientation. Let me give you an idea what I'm talking about. If I have, I don't know, what's with these markers? This is right out of the box, unless somebody's trying to have some fun on my account. Try this one. If you just have a dipole on the z-axis, I want to mention this, please listen, you don't have to write that, just listen. I got a short dipole on the z-axis, and this is theta, and this is r. Then the E field in the theta direction would be a sine. Y'all follow me in that? Right? Everybody? Now, if they do something like this, and they put the E field, and this is the x-axis, and this is the y-axis. Do y'all follow me now? And then I measure the angle from the y-axis. See, normally it's measured like this would be phi. Y'all follow me? We're looking right down the z-axis. If they put the antenna in this direction, then the angular variation would be a cosine of this angle right here. And I'll call it theta prime. Y'all follow me? Because the sine of that angle is the cosine of this thing. Now, I'm not going to spend much on this. So, anytime you see sine or cosine in there, it's a short dipole. And it means it's an easy problem, too, usually. So, now, I want to go through this with you. That's the E field. Y'all, Grant, give me that, right? If I want the power density, I think I wanted the H field next, didn't I? Correct, class?
Yeah.
All right, so the H field is nothing more than the E field in the theta direction, only it would be over eta, and it would be in the A phi direction. Does everybody understand that? This is a propagating electric field, and the E and H are always related by eta, the ratio of eta. How many understand that one? I've got to be absolutely clear on this, because all you had to do was take this, right there, which is IS e to the minus j. How about we just list beta here as 40 pi, so I don't have to keep writing it. Right? Times beta r. All right, then it's over r times the cosine of theta. And then it's just divided by eta, and it would be in the A phi direction. That's it. Y'all follow me? Now the direction of propagation is the coefficient at exponential. Do y'all see that, class? It's in the R direction propagating. And therefore, E cross H has to be the direction of propagation. E is in the theta direction, right? Cross it in H, you get R. Y'all follow me on that? How many understand that premise, all right? So just listen to me on this. So, I've got, this is H. Now to get the average power density, you can do it a lot of ways. This is the average power density. You can take 1/2 the real part of E cross H conjugated, right? You can do it that way. It just gets rid of the E to the J business, right? Or I like to do it this way. If we're talking about propagating magnetic fields and electromagnetic fields, magnitude of E squared over eta, it would be in the AR direction. Do y'all agree with that? Follow me? How many understand that? Right? I just take the E fields, propagating, square its magnitude, divide by 2 eta, bang, I've got the power density, the average power density, right? And when I say average power density, I'm sorry if this is a misleading term. In Dr. Wentworth's book, he uses average power density. I prefer the average Poynting vector. Remember I gave you that S symbol, but again, I didn't write the book. Now, the problem with average is, well, if all the power is radiating, I divide it by 4 pi r squared, that would be the average. That's absolutely right for an isotropic antenna. Average power density implies it's the power density of the wave in the phasor form. It would be like taking the RMS voltage times the RMS current, all right, back in the power, or RMS E field times crossed into RMS H field conjugated. All following that? So it's average power density, it does vary. What that means, I can literally take this E field, square it, so I get IS squared, right? Then I get, forget this term, because it goes away, it's a phase term, cosine squared theta, then I get R squared, and I'll put eta here, and I'll even put eta naught, and that's the intrinsic impedance of free space, 120 pi. You could have left it as eta. Do y'all follow me? And I give you credit. And it would be in what direction? The AR direction. Now, a lot of people are bad about putting directions. That's the unit vectors. Please, from now on, do that. I hate to take off credit for something like this, but I have to. How many have had Dr. Gross? Bless you. Because if he's done one thing to me, he's taught me that label your axes, always be attentive to detail, and other than driving me nuts about his neatness, he's right about a lot of that stuff. I'm being honest with you. If you get in the real world and you get notes, what? There's no axis. What idiot would do that? And then you realize you were like that at one time. But anyway, that's the power density, and it's in watts per meter squared, right? Now, that's the average power density, right? What's the normalized power density that we need, class? We need the normalized power density to get the directivity. Do y'all agree with that? How many understand that? At least I saw that formula down over and over, but a lot of people got confused. How do you get the average power density? That is the power density, right? Or normalized power density. So what does normalized mean in your own words? There's no wrong answer. By the way, tremendous game. I'm not used to having heart attacks with Georgia Tech, or Georgia, whatever state and stuff like this. I mean, I wasn't prepared. Give me a little more. Did y'all watch this game?
Yeah.
Holy mackerel. My dog was going crazy. My neighbors were. I didn't go. I didn't think, oh, by halftime be over, I have to run home anyway to watch the other games. Was I wrong? But anyway, congratulations. Enough said about that. Try to give him moral support. Our coach, I don't think, is very happy with the report. Anyway, y'all follow me that? What do we do with this, guys? To get the, I'm after the normalized power density. What is it? That's really what? It's the average power density, right, divided by the maximum value, right, of the average power density. Do y'all follow me on that? Yes, sir.
Where'd the 2 go, the 1/2?
You got left behind because I'm going to normalize it anyway. But That is the power density, you're absolutely right. What do I do, class? Come on, you know. Don't you answer. Nobody in the front row answers. Well, what does normalized mean? I try to get that across. Maximum value 1, right? And normalized power density will only be a function of angle. Let me make that a little more clear. This is the normalized average power density. Dr. Wilber's book just calls it. And it will only be a function of angle, has a maximum value of 1. Now look, you see how the cosine squared exists there? What's the maximum value of cosine squared? 1. What's the minimum? Right? That's it. That's the range of possible values. When you normalize it, the greatest possible value is that, right? Is squared over this, 2a. When you normalize it, you simply get cosine squared of theta. Y'all with me? Give me a show of hands if you do, because this is going to come back at you. It's probably on me for assuming you saw this fairly well and you didn't. All right, now we wanted to get the maximum directivity, right? That was one of the things, correct? We've got H field. Now then we got power density, so now we need this. Well, that's equal to 4 pi over, normally Dr. Wentworth spoke, he'll call this omega sub p. I like writing it out over and over. I mean, because I know I'm going to execute, so I just write it out. This is a double integral of the normalized power density, or cosine squared theta, times d omega. And if you did those problems with calculating the maximum directivity, you know that is going to have the form of what? Sine theta d theta d phi, correct, class? The only thing you have to do is make sure you get the limits right at this point. The d theta integration goes, I always say, from the north pole to the south pole, or from 0, theta equals 0, to theta equals 180 degrees or pi. Do you follow me on that, class? From 0 to pi. And where does phi go from? You start at the x-axis, you're in the xy plane, it goes from 0 all the way around to 0 again, or 360 degrees, or 2 pi radians. You follow me? Make sure you have a visual on that. From 0 to 2 pi. Okay, now I'm going to just show you this integration my way. I do the outer integral first. So when I integrate d phi here, there's nothing inside this kernel of integration that varies with phi. So when you integrate d phi, you get phi from 0 to 2 pi is just 2 pi. So I have 4 pi over 2 pi. Then I have the integral from 0 to pi of cosine squared theta sine theta d theta. Do you agree with this, class? Here at this point, I saw people do one thing that troubled me, and I think it was just panic. I saw them just take cosine squared and make it 1 minus sine squared. I'm like, why? I mean, this is, if you let u equal cosine squared, the derivative of u would be sine. Correct, class? So let me just break this integral out. If I have from 0 to pi of cosine squared theta sine theta d theta, and I let u equal cosine theta, du is equal to minus sine theta d theta. That's the simple substitution. But your calculators, if you ask, how many have symbolic integration capabilities on your calculators? No? No? Or you do? Most of you don't, really? How many have, what is it called, the Inspire? Is that, you have the Inspire 89?
TI Inspire.
Yeah, TI Inspire 89.
Yeah.
Does the TI X Pro do it or not? Anybody have that?
That does non-symbolic integration.
Non-symbolic? But you don't have to do it symbolically on this one. It's fixed bounds, but you can do it symbolic. Anyway, if you do this, what do you get? This is without, this is just brute force. This is going to be what? The integral. Now I have what? U squared. This is BU, but there's a minus sign, right? Do you agree with this, everyone? And then what? I substitute 0 for cosine of 0 is 1, right? And then I have cosine of pi here is minus 1, right? Isn't that right? How do I get rid of that minus sign in front of this business, class? Anyone?
Flip it down.
Yeah, just reverse the limits and it gets rid of the minus sign, correct? So I'm gonna do that. Make that minus, make that plus, get rid of this. And that's simply u cubed over 3 from -1 to 1 or 2/3. Isn't it, class? Do y'all agree with that? So if that's 2/3, this is 4 pi over 2 pi times 2/3 or simply 3. That's the maximum value. That's all it was meant to be. It was meant to be sort of a gift, but I don't know how people somehow thought it was a swindle on my part or something. I was trying to really confuse you. I wasn't. I promise you. I don't do that on quizzes. They're straightforward. If you've done the homework, you should be able to do these things fairly well. Just don't look like, just limit yourself. Oh, that was on the last homework, the first 3 problems. I know they're going to be on the quiz. If you do that, you're fooling yourself. You have to know this stuff fairly well. But it's straightforward if you do. After that, I asked for total power radiated, didn't I? Now, you can get that a lot of ways, but I'm just going to mention a few. You got D max here, right? Listen to me now. You agree with that? You've got D max. You also have the normalized power, right? Therefore, you can say, well, let's just put it this way. You can say total power, or the average power density, would be equal to D max. This won't get you where you're going unless you use radiation resistance. It's D max times the normalized power density right here. That would be the directivity. Then you would divide this by 4 pi r squared times p rad. Now here's really what I'm telling you I'm doing. You don't have to write this down. If I take p rad over 4 pi r squared, that's the average power density, right? I mean, that would be for an isotropic radiator, correct, class? Then the directivity sharpens it. The maximum value would be D max, then you multiply that by the normalized power density. That's the directivity at any angle. The problem is you don't know p rad, right? Now, you can get, some people did this. And unfortunately, this is on me, because if you did put down, well, I know the radiation resistance, since I did say short dipole is 80 pi squared, the length over lambda squared. You could have gotten it that way, and then you could have said P rad, and I gave you credit for this. P rad is equal to 1/2 I naught squared times the radiation resistance. You could have done that. The problem is you don't know the length. Y'all follow me? I did not specify the length. I said short. How short? But you got credit at least if you thought in that direction. Now the way you get it is, for this one, I know this is the average power, don't I, class? I want you to listen to me on this part. Did you have a question? Okay. I want you to listen to me on this part because it's important. You all see this is the average power density. Do you all agree if I integrate that over the surface of the sphere, that I'll get the total power radiated by that antenna? How many understand that? Are you with me on that? If you got the average power density and you integrate it over the spherical surface that really encases the antenna, it has to be the total power radiated. So I'm going to do that over here, and you're going to see that integral pops up again. That's what makes it easy. So over here, good. So I'm going to say P radiated. Now, if you didn't get this right, make sure you follow me. This is the integral of the total power density. Do y'all agree this is the power density right here, right? So I'm going to put it down. IS here squared. It's divided by 2 eta r squared cosine squared of theta. It's in the AR direction. And it has to be dotted with a differential surface element in spherical coordinates. I assumed you know this stuff, but I think maybe you don't. When I talk about the differential surface area on a spherical surface, that would be r squared sine theta d theta d phi. R is held constant. So this, it would be in the AR direction, but it would be r squared sine theta d phi Now, this is, right here, that's the differential surface in spherical coordinates. How many of you know that? How many again? A lot of you don't, right? If you don't, I'll put that up there, but I'm gonna give you some problems with it, because this should be something that you're very familiar with. A differential surface is like, if it's in the xy coordinates, the magnitude would be dx dy, right? And the direction would always be perpendicular. If you're above the plane, it would be positive AZ. If you're below, it would be minus AZ. Do y'all follow me? Surface always has a magnitude and a direction. Then the limits, well, for the first one is theta, that goes from 0 to pi, and phi goes from 0 to 2 pi. You agree with this, everyone? Now watch this part. How many agree that that would be the total power radiated, at least if you could execute that integration? You all see it here now, guys? I gotta make sure you at least understand what I'm doing. I mean, you're good with that, yeah, you may not like it, but that's it, right? Now, you all see that all this stuff, there's a whole bunch of constants. AR is 1. Take note, you see how the R squared goes away? It'll never be a function of R. If it was, it wouldn't make sense. How can further away you go, you get more power radiated or less? Y'all follow me? Unless there's attenuation. Now what am I left with for P rad? Well, all the constants come out in front. I have IS squared, I have 2 eta naught, and then I'm going to go ahead and integrate phi from 0 to 2 pi, bring out the 2 pi here. And now I'm left with this again. Now I have that cosine squared of theta, sine theta, d theta from 0 to pi. You all agree with that? I did the outer integration first from 0 to pi. Now, y'all know we just did that one, didn't we, for d max? Everybody with me? So that's what? 2/3, isn't it? How many remember it's 2/3? You can just put that in there. And that's the total power radiation, no matter what form it's in. I didn't care. You can put eta naught as 120 pi, you can cancel a whole bunch of stuff, but that would be it. You follow me? And the trick with this one is you have to see that that integration, the total power radiated, had the same the same form as the D max. And if you saw that, you were fine. A lot of people did have trouble with this one. I'm going to be fair about that. I'm just telling you, I guess it's on me for assuming it was fairly obvious how you go through the steps. But make sure you know this. You will see this on your test. Now, didn't we discuss having the date of the test today, discussing it, right? All right, you've had time to, I assume you've had time to look at your schedules and talk. Do you have any suggestions? Anytime in the next 2 weeks, you can wait and have it later if you'd like. Anybody want to give a date? I don't want to pick it for you. Usually people, how many have you before here? Usually people tell me dates. Do you have any dates?
So I put a group meet poll for October 13th and 15th.
You put a poll up already? How many saw the poll? Some didn't. What is it looking like?
It was fairly even, but
Between the 13th and the 15th, 15th had more votes.
Well, let me ask you this.
Yeah, the
Since it's
15th
October,
had
you said?
more votes.
Yes.
How about this? Since we're not a full house yet here, we got people missing. Why don't you do this? If you're okay with it, we'll vote today if you want. But why don't you next time do that poll, make sure everybody can see, and just give me the results. Is that fair with everybody? I mean, I'll do it here now if you want.
I don't care either way.
8 for the 15th, 5 for the 13th, and 1 for other.
We can do it. You can do a poll right now.
Do a poll right now,
All right.
who's here.
Everybody
Poll
did
right
it.
now.
I don't think everybody got the.
Yeah.
You didn't?
I'm not in the group.
Not everybody got the poll, so.
Oh.
So it's not really fair.
Wait, that can't be fair. All right, I tell you what, how many people got in 2, 4, you're here, and I did say we'd vote today, didn't I?
Yeah.
2, 4, 6,
Did I put that
8, 10, 12,
14th.
And then this. I guess that's not.
22, all right, you got more than half the class. You're here, you get your vote. All right, what dates would you like up? We'll
13th
vote
to
on.
the 15th of October.
What is it?
13th to the 15th of October.
October 13th, October 15th, is this a Monday?
That's a Wednesday.
Wednesday?
Wednesday and Friday.
This is a Friday?
We have a quiz that Thursday in economy, if anybody.
Any other-
cares about that.
Uh-huh.
Any other dates? Any other dates?
I don't want a Monday
Oh.
test.
Okay, here's what I want you to do, just vote once, please. Would you help me count? All right. Yeah, just count hands when I get.
Sure.
All right, if you want it Wednesday, October 13th, one hand, one vote. Hold it up, let me get the count. I got 1, 2, 3, 4, 5, 6, what is it? 4, 5, 6, 7, 8, 9, 10, 11. 11?
Yeah, and then
12.
add me, so 12.
12. All right. 15. This is going to be close. Hold them up, one hand. I got 2, 4, 6, 8, 10, 11.
I got 11.
Wow.
How many people did we have in here? Did we count 23 people?
We do, and I don't get a vote. But I tell you, that's razor thin right there.
Wow. So
Well,
the people that's in economy and not in economy?
All right, it looks like, unless there's some overwhelming reason not to,
Damn, I was tired.
it looks like it's the 13th. Okay? Yeah.
On the topic of scheduling, are we gonna have a quiz this Friday?
Are we gonna have, well, we-
I'm just curious. Some people are going out of town for the game.
I mean, if you got a legitimate excuse, I mean, if you have, whatever you call it, a university-approved excuse, then it's fine, but I mean, it's supposed, every Friday we have a quiz. I mean, I'm just level with you, I know he has a university-approved excuse, and you do too.
Can I change my vote to the 5th?
Oh, no! No! Voting's closed!
No,
Voting's closed.
I have a really good reason. I have an interview at 1 with a company that I really want to work for. So
Well,
I would have to,
All right.
that would be
All
really
right, I'll tell you
tough.
what I'm gonna do, just because this is getting out of control. We're gonna do this on Wednesday. You go ahead and rally your friends to be here, bring protest signs, Wednesday or not. You can have some fun with this. All right, fair? I mean, it's too close, honestly. When I see one vote difference, normally I toss a coin, and then they all yell at me for. We'll do it Wednesday. Would you do me a favor, guys? All of you remind me first thing, and then you can get in fist fights afterwards.
No, her job confirmed her.
It's usually not that close, I'm gonna tell you that. That's as close as All right. That was a quiz. All right, and quiz. Now today, I've got stuff to cover, but I'm gonna try to make this as clear as possible with you. Right now, we've done short dipoles and we've done small loop antennas. For both of those cases, any small antenna, I better do it better than that. Any type of small antenna like short dipoles, small loops, etc. Any type will always have a directivity. The directivity will always be equal to some, it will be exactly 1.5 for all short dipoles. And it will be times the angular function. Now, almost always, if the antenna is like, if it's a short dipole, this is the z-axis. If the antenna is on the z-axis and this is theta, this will be times the sine squared of theta. That's the way it is always. Now, if it's a loop antenna, the loop antenna is in the xy plane, it's the same thing. 1.5 times sine squared of theta. That's for any of them. The difference is between a loop antenna And a short wire antenna is the radiation resistance. Y'all follow me? So if you have a short dipole, they call it a Hertzian dipole. And here is L less than lambda over 10, typically. Then R rad on this one is equal to 80 pi squared L over lambda. Now, if you have a loop antenna, the form, I would give this to you. And by the way, I would give you that if you want on a test. I'd give you that, all right? I'll give you the radiation resistance for different antennas. But for a loop antenna, it's going to have a different form than this, but it's going to be small. Right? So this is the thing that you care about. Once you have whatever it is, the radiation resistance is, then you get the power radiated. And that's 1/2 magnitude of I naught squared times R rad. Radiation resistance. Now here's why I'm a little hesitant to put down a loop. Dr. Wentworth's book has the radiation resistance for one turn. You hear me on that? Almost always small loop antennas are multi-turn. And therefore the resistance will be n times the single loop. And that's the reason I don't put that on there. I mean, I don't want to use Dr. Wentworth's because people just grab it. Depends on the number of turns. I put this on one note. Do y'all remember that class? It will affect it, but this becomes the key. You want to get P radiation because once you have P radiation, anything else you want is easy to get. For instance, if I had a short dipole and I'm at a given range for a given angle theta, and I knew the length of this, say it's the length of this, from the length, I could get the radiation resistance. From the radiation resistance, the next thing I can get, regardless of how it's connected, if there's a voltage source or not, if the current's given, doesn't matter. From there I can get P rad equal to 1/2 I naught squared times R rad. Now, if there was a voltage source driving that current, then you would take the radiation resistance and divide the voltage source by that to get the current. Do y'all hear me on that? Here's something that they don't tell, Dr. Wentworth didn't say. In the short dipoles, they aren't just strict radiation resistance as far as their input. There's an imaginary component. All right, there is a actual plus J something reactance that is a function of length that Dr. Wentworth's book doesn't get into. So normally speaking, when you have short dipoles, their impedance is so small that the other impedances in the circuit are the thing that will limit the current. All right, you can more or less usually replace those by a short circuit, usually, all right? And you can figure out the current from there. Follow me on that, class? I don't give you trick problems on that. Anyway, from I you get P rad. Now once you have P rad, then at any range R, you can find the average power density by saying it's the total power radiated. Then you divide that by 4 pi R squared. Now I have the average, I have the isotropic radiation, right? If it was just radiating the same amount in every direction, that would be the radiation density, right? Y'all follow me? Now I multiply it by the directivity. So if it's a short dipole, it would be 1.5 times the sine squared of theta, where theta would be the angle if it was a straight wire dipole with respect to the vertical axis. Let me be straight with you. I don't give you trick problems on this. I'm not going to take this dipole, all right, and bend it at like 40 degrees this way, right? Or something where I really try to throw you a curveball. Not going to be like that. But you'll have to understand the basics. Right? So now, if that's the power, do y'all agree that's the power density in watts per meter squared? All right, if I have that, here's a question I almost always ask. I'm out at a given range R for a given angle theta. How do I get the electric field? Anyway, I usually ask for the electric field at this point out here. I want the electric field at some range R. How do I get, and it's for some theta? Anyone? Did you going to say? Well, what is the power density equal to? I put that down line.
1/2.
I know that what? This P-ab is what? 1/2, right, magnitude, you were saying, you're right, over eta, right, in magnitude class? If we, do you all agree with that? So if we have the average power density, and we get it from this equation, that's why the gain or directivity, I'm using gain and directivity interchangeable. Okay, if I gave you an efficiency difference, then you'd have to use efficiency times directivity to get the true gain. But now I have this, so I just say that the E field, right, is equal to the square root of 2 times eta times the average power density. Now I got the E field. Now you can, yeah.
Where is the D equals 1.5 sine squared theta? Where's that coming from?
For all the short dipoles, the maximum directivity is 3/2 or 1.5. Do y'all agree with this, class? Remember the short dipole is
So that means that all the E fields you're gonna give us are gonna be a component of sine theta?
or what?
So that's true if like the E field has sine theta in it instead of like,
E field will be a sine.
Okay.
See this square root of that's
Yeah.
gonna give you a sine theta. Do you agree with that?
and it's always gonna be like that, like on
Always.
Okay.
Yeah, and I gotta tell you this. This came when we did the short dipole and actually got the directivity. It had a maximum value of really 3/2 or 1.5, and it varied as the sine squared of the angle, right? So once you find the maximum directivity, which is 1.5, the next thing you do is take the normalized power density, which was sine squared of theta, and multiply that to get the actual directivity for any angle. That's how I'm getting this. I can put it this way. This D right here is really D max right here times the normalized power density that was used in the calculation. Now, that right there, that's the E field. Now what we're going to do is this. This is really short dipoles or small loops. In a nutshell, the key thing is find the power radiated, and then going right to this equation, I'm giving you right here where you take the gain, or you take the total power radiated by 4 pi r squared. That's how much would be there isotropically, and then you multiply it by the sharpening effect or by the directivity at a given angle. Okay. Now, when we have dipoles that are long, this is the next thing I'm going to do. I'll show you what happens in long dipoles. I'm going to get right to the point in 3. So now Dr. Winters' book always puts them on the z-axis. This is the origin, and it's going to say I'm going to have an antenna, but it's no longer short. The antenna is going to stretch from minus L over 2 to L over 2, and now L is going to be greater than lambda over 10. It can be a lot greater. But this is the length of the antenna. Y'all follow me? So how do you do that? Well, here's the trick. You have to know the current distribution. So if I was to plot in this axis, say on this axis, the magnitude of I as a function of Z, you don't know this yet. Current has to go to 0 at the ends of the antenna. If it doesn't, it makes no sense. Just think about Kirchhoff's law. Wherever it goes into comes out of or stays there, right? Well, if you got something going into and nothing coming out of it, it's staying there. So that means there'd be an enormous charge ball there. And there aren't. Here's the way the current looks like in profile. It does something like this. If that is the magnitude of the current, it'll be symmetric about Z equals 0, and it'll look like this. And this current is given some value I naught, whatever that is. Then it will be times the sine. And here you'll have, the way he does this is beta. I don't know if he has a 2 in his book or not. It's going to be L or Z minus 1/2, but I gotta just make sure. There's two ways to do this. He's going to do L over 2 minus Z. All right. So here, he has beta by itself, and then he has L over 2 minus, and just put magnitude of Z. And let me explain this for a second, and I think you'll appreciate it. So when I look at this, right here, beta is still 2 pi over length. This is in his text, but I have to explain one thing to you. Now, I told you one of the key things is that the current had to go to 0 at the ends of the antenna, right? Well, if you go in here and you let Z right here be equal to L over 2, you have L over 2 minus L over 2, which is 0. 0 times beta is 0, sine is 0, 0. Checks that box, all right? What you don't see, unless you play with it, it isn't a maximum right here. It depends on the value of L. It could be 0. Right? Normally when you drive these antennas, they're called gap driven, you put a plus to minus voltage there. Usually you literally have a small little gap and you put a plus minus voltage, it drives current in a symmetric way here. But if this current goes to 0, it's a theoretical current, then that means the impedance would be infinite. And the truth is it never does happen that way, but I gotta tell you this. The way they arrived at that is not from solving Maxwell's equations in an exact form. It's basically an approximation for a numerical solution. However, it's very close, all right? And it depends on the wire radius. So when you have these thin wires, as they get fatter, things change right there. I'm just telling you this, and this is the reality. But this is pretty good. So if we have this is L, that's beta, and that'll work. And if that's the current, here's the way we go about getting the E fields. We say if we have any little bit of chunk of current, what we'll do is this. We're going to come out, and this is the way he does it in the book, a distance R. And here's going to be my little chunk of current. I use the purple to define it. It has an I of Z. It's not constant anymore, it varies. It's at a height Z. So this is going to be at height Z. And there'll be a second R, which I'll call R prime, right here. Now, R and R prime are about at theta. And we're going to assume that the length of the antenna is going to be a whole lot less than R or R prime. So in other words, you're in the far field. You're a long way away. Y'all follow me in this class? And if you're a long way away, can you see how R prime and R will be about parallel? Just let them go a mile away. They're basically parallel to each other. Now there's an importance. So when I take a look at this, right here, this little chunk, it gives way to a differential electric field that I'll call DE here. And I can say that that differential electric field will be equal to J eta beta. This is going to be as if it's a short dipole. Y'all follow me? Of length Z times I of Z over 4 pi R prime. Then it's going to be times the sine of theta, right there. And it's going to be times e to the minus j beta R prime in the A theta direction. Let me explain what I've done here. If I, and it's times dz. If instead of dz, I put a length L in it, this would be the electric field from a short dipole. You all see that? Remember that, class? What I said is, all right, I got a little differential chunk there. That's the differential electric field. And here's where some of the stuff happens. When I look at this, I know these two guys are going to play a critical role. So I'm just going to show you up here. If I have an antenna, and I'm talking about this being the origin, and this is my point where I have I of Z right here. This is R. Now, maybe, let's do it this way. This is gonna be R, and this is R prime. This is at a height Z. What it's gonna say is, for these two, all right, 1 over R prime is about equal to 1 over R. In other words, they're about the same magnitude if we take 1 over. Think about 1 over a mile, and then 1 over a mile plus an inch. Does that make sense? They're about the same. So that means this guy I can replace by R. Now the next thing is, I know how that varies, right? I know that's going to be I naught times the sine of beta times really Z minus, it's really going to be right there, L over 2 minus Z magnitude. I know that. Here's the tricky part. See that R prime there? Now I want you to just watch this. You don't have to recreate this, but you have to appreciate it. When I come down here, that's the right triangle. Do y'all agree? Matter of fact, let me do it this. That's lousy right triangle. What I'm trying to do is show you. Let me do it this way. Here. Oh boy, these are not exactly the way I wanted to do it, but I'm trying to get these as parallel as possible, but this would be R prime. You're gonna have to just assume this. When you look at this, if this height difference here is Z, and this angle from here to here is theta, right? Right there, then this distance right here is gonna be Z times the cosine of theta. Remember, if this height is Z, this is a right triangle here, then this distance would be Z cosine theta. I want you to just think about this. What happens when theta goes to 90 degrees? Do you see how this thing will go to 0? And then there is no path difference between R prime and R. So the thing I can do is say that R prime is actually equal to R minus Z times cosine of theta. Now, I'm not going to have time for this today, but I want you to appreciate this. I'm going to take this and stick it in here. And when I do, I can factor out that e to the minus j beta r. I'll do this next time and show you. And after you do the integration, which is a little tricky, you're going to find out that the E field from an arbitrarily long dipole will be equal to this. It'll just be J60 times I naught over R times e to the minus j beta r, and then it's going to be times this angular function, cosine of beta L over 2, cosine of theta, I don't have time today to prove this, minus cosine of beta L over 2, this whole thing divided by the sine of theta, and it will be in the A theta direction. Now, I'll put that on one note for you. In Dr. Wilmer's book, he doesn't show this exactly, and I'll give you some basic stuff to do some homework. And I'll try to be as clear as I can about where we're going with this. The H field from here is going to be obvious, but really the thing is, when you look at this angular plot right here, even though it looks like a mess, MATLAB will allow you to plot that thing very easily. And what we're going to do is plot the power patterns that are normalized in a second. All right? I'll see you on Wednesday.